Now let us recap about what we have done with the previous session. We started with current electricity, where we learnt about three important terms of current electricity, without which we will not be able to understand the whole chapter I told you. They are nothing but current, as you're seeing over here, and the next thing is going to be voltage, and the third term is going to be your resistance. The current, as we defined in the last class, it is going to be the rate of flow of electric charges within the given time. The given time means rate. And if it is going to start moving from a negative terminal towards a positive terminal, we used to term that as electronic current. And when it's going to start moving from the positive terminal towards the negative terminal, we used to term that as conventional current. And when you're coming for the next term over here, that's nothing but what we have over here is potential difference. The potential difference is nothing but the amount of heat energy lost by the electrons as they are going to make the appliance to work. Or the definition for that is the amount of work done to move a unit positive charge from one point of the circuit to the other point. As you're seeing, the electrons are gaining the energy from the battery and they are going to go through the circuit. They are getting into the appliance, they are making that appliance to work. That is, the bulb is glowing here. After making the bulb to glow, they are coming with empty hand. That means that with a very less amount of energy they are coming out, as they spend the energy in making the bulb to glow. They are coming back to the battery, they are recharging themselves with the energy and they are moving. So from here, what is the energy they started with is going to be 1 electron, 6. When it's going to get into it, it makes the 6-volt bulb to work, and when it's going to come out, it's going to have a 0 energy. That means that the 6-volt is going to be the potential difference what you are going to have it over here. That is what is the dots are representing here. And when we are looking at the third term is nothing but resistance. Whatever you have in a circuit which opposes the flow of electric charges or the electrons is called as resistance. We have done, and we have done about the formulas for the resistance as well, that are nothing but based on the dimension. You could able to write the resistance, the dimension of the conductor. You can write the formula for the resistance as rho times L over A, and it will be given with the unit of ohm, the person who found it, right? Here rho is the specific resistivity, L is the length of the conductor, and A is the area of cross section. We have done. Then by connecting this current, voltage and resistance, the relation which is given by ohm is called as Ohm's law. What is this Ohm's law is giving us is nothing but, as I told you, voltage is directly proportional to the current passing through it. As you're seeing, the amount of push, that is the energy given to the electrons or making them to flow, but there is something which resists that movement, which is called as resistance. So this relation I'm trying to show it off over here in terms of equation. V is proportional to I, and that I flow will be decided by the resistance, so that you can write that as V is equal to IR. And you could able to remember this with the help of a mnemonics I told you. The vegetarian peoples are called with a name Iyer, right? So that with that small mnemonics you could able to remember this equation. I'll just show you one more analogy for the Ohm's law over here. As you're seeing, the electrons or the cats over here, and the cat wants to get the cheese, right? What is the one they have in the middle? That is nothing but the cats. The rats are wants to move towards the cheese, but they have an obstacle in the middle. They are nothing but the cats. So whenever the electron wants to flow in the circuit, then they have a opposition which is called as the resistance over there, which restricts the movement of them. But still the cats won't stay, they will start moving. The driving force for this rats are nothing but the cheese what we have here. Like the driving force for the electrons in a circuit is going to be the voltage what we are supplying, or the battery or the power source, right? So in this case we could able to define the ampere in this way, that is the number of miles per unit time that make it to the cheese. In the other way, ampere is nothing but the amount of electrons per unit time which is going to be driven by the voltage, right? Hope so you got this analogy and you will remember the Ohm's law easily, right? Now the term what we are going to start in today's session newly is nothing but the topic is drift of electrons and their origin of resistivity. What do you mean by this drift of electrons, and how do we obtain the drift velocity we will do, and how it is going to be connected with the resistivity that we are going to do. So as you are seeing over here, generally if you are going to take a conductor, so what you are seeing is going to be a conductor of copper, right? The copper is having the electrons inside it which are all called as free electrons. Free electrons means they could able to move freely in the circuit in all the possible directions. That means that they don't have a velocity. Velocity means speed in a particular direction. As the electrons are in a random direction over here, they do not possess velocity when there is no electric field is being supplied to it, right? Now whenever a particle is going to be in motion, then it must be driven by a force. That force will be given by the formula F is equal to ma from our Newton's second law of motion, right? So F is equal to mass times acceleration, which I'm taking that as the equation 1 over here. And if you're going to look at the next one over here, you could able to see the same copper conductor, the same free electrons you could able to see. But what is the thing done over here is nothing but I just supplied some electric field. As a result of this electric field, you could able to see the electrons are drifted towards a particular direction. Now they are not random, they do have a particular direction associated with them. They are following a particular path, that is they'll start from a positive to negative, or they will be moving from negative to positive. They are going to start following a path, right? As the electrons are going to be charges, and because of this electric field supplied, they are going to be getting this force. We used to define this force due to the electric field as QE, where Q is the charge and E is the electric field supplied. And as if you know what is the charge we have is going to be the electron, so we are substituting the Q as minus E over here. Could you able to get that? Let me explain it. The term why the electric field and the drift velocity, that is the velocity with which the electrons are drifted, or opposite in the direction of the electric field. The reason for that is when we are supplying electric field, it means that we are connecting a battery. When there is a battery is going to be connected, there will be a positive terminal as well as there will be a negative terminal. Now if you are thinking about it, the positive and the negative, the electrons are having the negative nature. Because of the negative nature, they will be attracted towards the positive only. Yes, that's the reason when you are supplying an electric field, the electrons will be drifted in a direction opposite to the electric field supplied. That's one more reason why we are using a minus sign over here, right? Now I'm taking this as equation 2. Now from the equation 1 and 2, both of them are the forces which is deriving the electrons only, so both of them must be equal. So in that case I'm taking that ma is equal to ee. That what we have got from the equation 1 and 2. Just by rearranging it, I'm getting a is equal to minus ee over m from Generally, the normal equation for the acceleration is nothing but change in velocity over change in time, where the change will be represented by the Greek letter delta. So I'm rewriting that as delta v over delta t, right? Once again, a small rearrangement. I'm taking the delta t over this side. So the change in velocity will be given by acceleration into change in time. Where the change in time, what you're going to have here is nothing but the relaxation time. What do you mean by this term? Relaxation time is nothing but, as you're looking back over here, the electrons in a motion, right? So when the electrons are going to get into motion, this electron, one electron may get collide with the other electron. So without colliding, how far it could able to move, or how much time an electron could able to move in the circuit without getting collided with the other electron or without getting disturbed is called as the relaxation time, what you're seeing over here. So that relaxation time now will be represented by the term, Greek term tau over here. And what is the change in velocity we have? That is, initially it's a random speed, then it has been changed into a particular direction speed, which is called as the drift velocity, as the electrons are drifted towards a direction with the help of the electric field supply. We are writing this change in velocity as the drift velocity over here, which is represented as Vd. So del V is being replaced by Vd, and A, we have the value over here, E divided by M. I'm substituting it, and the delta T is being replaced by the term tau over here, right? Now I'm taking this as the equation 3. Now what we are going to do is, the current formula, we know that the current is going to be given by the formula according to Ohm's law, I is equal to V over R. And with the general definition, that is the basic definition of the current, we know that it is going to be the amount of charge in the given time, right? Now we are going to rewrite the same current. See, I'm going to rewrite the same current when we are going to come for a conductor. So I'm taking a conductor which is going to have a length of d and area of cross section A. The charge which is flowing inside a conductor, we know that very well, the electron, and all these electrons are going to be drifted with the velocity Vd, which is a drift velocity, right? So all these terms I'm going to include over here. The amount of charge which is flowing through the circuit is going to depend upon the same factors over here, because we said that resistance is going to depend upon the dimension of the conductor what you are taking. So if resistivity is going to be decided by the dimension, then obviously amount of current will also be decided by that. So we are rewriting that in terms of the dimension of the conductor. Now the total amount of charge in the conductor will be given by Ne. Don't get confused with this term Ne. Hope so all of you remember your first chapter, quantization of electric charges. Whatever the total number of electric charges you're going to have in a circuit will be given by total charge is equal to integral multiple of the charge of electron. That is, whatever the number of electron you have into the charge of one electron will be giving you the total charge. That's the same thing I'm taking over here, right? So what is the next term you have here is nothing but area of cross section of the conductor and the length of the conductor. If you are having more length, for example within 1 centimeter, here only one electron could able to stand. Let me consider this portion alone. How many electrons are here in this length? In this length only 4 electrons. But when I'm going to extend the length over here, I could able to see few more electrons are available in the length, right? That's a reason why we are adding the length over here. The length of the conductor and the amount of charge will be directly proportional to each other. As the length increases, number of charge availability over there will also increase. And you look at it over here. I'm taking half of the surface over here. How many electrons I have? Only 1. If I'm taking the whole surface, I have 2. So if area of cross section increases, the amount of charge available will also get increased. That's the reason why we are including the area of cross section as well as the length of the conductor over here. All of you could able to understand what I'm trying to convey, right? So when you're going to look at the terms over here, now I have written the Q in terms of the dimension of the conductor. Q will be given by NEA into D. And we know this equation already, or we know this relation already. Velocity will be given by the displacement over time. Displacement over time. We know this, right? Now if I want the time from this, what I have to do? Time will be given by displacement over velocity. That's the same thing we are taking over here, as the velocity of the electron over here is the drift velocity. We are changing that as Vd. Here the d represents the distance which the electron travels, that is the length of the conductor. Okay, now what we are going to do is this q value and this t value we are going to replace in the basic definition of the electric current. That is, q is going to be replaced by NEAD and t is going to be replaced by TVD. When you're going to look at it, this d and this t will get cancelled, so the final expression will be like this. That is, the I is going to be given by NEAVD. So this is the formula for the current in terms of drift velocity, which I'm taking that as equation 4. Now we have done about this relation already in the last class. The current density is going to be given by the amount of current flowing in the given area, and out of this we know the current value from equation 4 over here, that current will be given by NEAVD. I'm replacing the I over here in the current density with that value NEAVD, right? Obviously what will happen, there is a denominator A over there, both of them will get cancelled, then as a result of it you will be getting the current density in terms of drift velocity. J is equal to NEVD, which I'm taking that as equation 5 over here. Did you get that? Okay. Now the next one, from equation 4 we know that J is equal to NEVD. I'm sorry, from equation 5 we know that J is equal to NEVD. And from equation 3, that is the drift velocity, we know that EE by m into tau, right? Now what we are going to do is, we are going to substitute the value of the drift velocity in the current density. So I'm substituting this value over here. Could you able to see that NE remains same? Instead of VD, I substituted this value over here, right? So by just rearranging it, what I'm getting, the E over here, where this NE tau squared m is nothing but the sigma what we are going to have. So the sigma over here is nothing but NE squared tau over m. All of them are constant. The sigma is nothing but the conductivity of the given conductor. That will also remain same based on all these constant terms of the conductor. That's why we are replacing that constant with sigma conductivity. Could you able to see that? Now we know this relation already. Rho is the specific resistivity, that is how much amount of resistance is going to be available in a conductor which is of 1 meter length and 1 meter square area. Similar way, if you are going to take 1 meter conductor of 1 meter square area, how much amount of conductivity will be there will be called as sigma. As conduction and resistance are inverse to each other, rho is equal to 1 by sigma, and finally we got the relation for the resistivity over here. Rho will be given by m over that inverse of this sigma, m over NE squared tau, right? Now what is the next thing we are going to do is nothing but mobility 3.5.1. What do you mean by this term? Mobility is nothing but, as we know, the electrons are going to have a random motion. As you're seeing the particles over here, they are the electrons. When these electrons are going to get into a free motion, the electric field is going to be supplied to it. As a result of the electric field supplied, they could able to get into a motion, that is they could able to move in the conductor in a particular direction. So how conveniently they could able to flow in a conductor with the supply of the electric field, that is going to be given by the mobility. If you want that as a definition, then the mobility of a mobile carrier in a conducting material is defined as the magnitude of drift velocity per unit electric field. That is how good the electrons are going to be drifted when the electric field is going to be supplied to it. Vd over E, where we know the value of the E already. What is the value of the E? We have seen it over here in this slide. You could able to see that. What is the value of the Vd? Minus E over m into tau. So if we are going to substitute it over here and I'm going to simplify it, obviously we are going to have the term E tau over m. Right? Now let us get into the next subtopic, which is nothing but limitation of Ohm's law, which is of 3.6. What are the limitations we have? Before that, where the Ohm's law is applicable? Ohm's law is applicable to such a conductors which is going to have a linear relationship between the voltage and the current. That means that what exactly we are going to do now, the Ohm's law is going to be applicable to conductors, means obviously they are not going to be applicable to the insulators as well as the semiconductors. But nowadays the overall electronic field is going to be based on the semiconductors only. So how the Ohm's law is not applicable to that only, we are going to look into that. As you are seeing here, you could able to see the first graph. Let me explain it in terms of a number, then I'll come to this points over here. You could able to see that initially I'm increasing the voltage. Voltage is nothing but I'm continuously giving energy to the electrons, but the electrons are not getting into a single direction. They are in motion as I'm supplying energy, but that will not be taken as current. They have to follow a single direction. That is not happening when I'm giving the energy initially. I'm pushing and I'm pushing and I'm pushing continuously. At one point of time, the electrons left the random movement and they started flowing in a single direction, which is defined as the current. So slowly they started following a single direction, which increases the value of the current over here. Could you able to see that? Slowly the slope got increases. But in a conductor, it will be a straight line. Whenever you are supplying voltage, automatically the current will start growing. So it will be a straight line. It's not a straight line over here. That means that it is the graph which is being for the non-metallic conductors. So Ohm's law is not applicable to the non-metallic conductors. It also does not apply the nonlinear devices such as Zener diode. When you are looking at this term diode, diodes are the devices which are going to work with the help of semiconductors. What do you mean by this term semiconductor? You would have been learnt about it in your chapter 14 about the semiconductor devices, like the triodes, diodes and all the vacuum tube stuffs, right? So let me give you a gist about it. Semiconductors are the materials which do not have a conducting nature at room temperature. So when the temperature of the semiconducting materials are going to get increase, as the increase in temperature happens, the electron will gain more amount of energy so that the valence electrons of the material will be started moving. That is which will now called as free electrons, like the conductors what we have. Right? So when the temperature increases, the general cases resistance will increase because the random movement of the electron will increase. But in semiconductors, when the temperature increases, that higher temperatures are only allowing the electrons to get into motion from their bound state. So the temperature increase will increase the conductivity over here, which is not applicable to the Ohm's law. Right? Because when the similar thing, if you're going to look at it, it will be similar like this. When the potential increases, that is you're supplying energy, the electron will not get into motion. You have to supply energy up to a particular level. After that, what will happen? They will start moving, which means that they will become free electrons and the conduction process will start. So for a particular level, this will be a horizontal line and then only slowly it will start increasing. right? That is why it's not applicable to the non-linear devices. Non-linear means what is the potential we are supplying, that and the I, both of them are not direct proportion to each other. If you are not having a direct proportion, that doesn't mean that inverse proportion. Direct proportion means it will be a straight line. Just for one increase, the other one also will get increase. Over here, slowly it will get increase. So you will be having a graph which is a kind of parabolic path, right? That is why the Ohm's law is not applicable to the Zener diode. And when it's going to come for the uh, temperature over here, the conductors what we have, the temperature of the conductors is going. So you are saying over here, it is true for the metal conductors at constant temperature, but it is not applicable to the conductors when it's going to be at a higher temperature, right? So if the temperature change, the Ohm's law will not be applicable, right? That's the same thing you're seeing over here for semiconductor. When the voltage increases, initially it will be showing a linear property and non-linear region. You could able to see all of them together I'm putting. So this is for a conductor, this is for a semiconductor, and the semiconductor, if you're going to heat it up for a longer time, then it will start losing its original nature, so which will go for a negative resistance region over here, right? Now let us get into the next part of this chapter, which is nothing but 3.7, resistivity of various materials. We are going to look at it, resistivity of various materials. Obviously different materials will have different nature of electrons associated with them. Because of that, the resistivity of them will also vary, right? So that's what exactly we are going to do. You could able to see the resistivity over here, different materials possess different resistivity, but there is a range for it. The metals are going to have the resistivity about 10 power minus 6 to 10 power minus 8, okay? But when it's going to come for the insulators, they are going to have the resistivity which is going to be 10 power 18 times greater than the resistivity of the metals. The semiconductors are going to have the intermediate resistivity range over here, right? And the next one what we are going to do is nothing but wire bound resistors and the carbon resistors. What we are going to do, wire bound and the carbon resistor, these are the two major resistance what we are using commercially. Let us explore about these types of resistors in the next class. Okay, now let us conclude what we have done with today's session.